This is the second lecture for Chapter 4, and in this lecture I'll discuss multiple integrals again, but in this case the limits can be functions. Thomas made the remark in his chapter on multiple integration that the hardest thing in taking these double and triple integrals is finding the limits of integration. In this lecture I'm going to give you the limits of integration. In future homework assignments and in future lectures we'll discuss finding those limits. So the reason that the limits turn into function is that the area of integration is bounded by a curve and not just by intervals in x, y, or z. So here's an example. Let's say this is the x-axis. Here, that happened, and this is the y-axis. All right, and you see here we have this semicircular region. What we're talking about here is a function of two variables. So here's the z where I'm going to put the function values. Here's my x, here's the y, and the region that I'm taking this over is some region here. And above this I'm constructing, let's see if I can do this with any kind of accuracy, but probably not. This is what I'm trying to take the volume over. Okay, so these would be, this height here is the value of the function, and the base is described by this situation over here. X is going from -5 to 5, and y is tracing out this semicircle. So now we need to know the limits in order to integrate over this region. The lower limit of x is -5, the upper limit is 5, because x varies continuously from -5 to 5. So that gives me limits of -5 to 5 for the x. Now for the y changes as x moves from -5 to 5. And here I'm specifying what that change is. As x changes, y changes as 3 plus the square root of 25 minus x squared. That gives me a semicircle with its center at x of 0, y of 3, and has a radius of 5. As you can see, if you have to find this on your own, you've got to find the expression for y in terms of x. So here are the limits right here. The lower limit is 3, and the upper limit is defined by this red curve is 3 plus square root of 25 minus x squared. This was a graph I tried to do over this semicircular region. You can see x varying from, I might end up with that straight line sometimes. Here's x varying from 5 to -5. I've rotated this 3D graph around, okay, and then y varies from 3 into that semicircular region. It sure doesn't look like it here. It's very hard to draw, even for the computer, I guess. But basically the idea is that the underlying region is that semicircular area in the xy plane, and you multiply that area times the value of the functions. Here's what the integral would look like. Say the function is x squared times y. The innermost that I've written here in the inside is the integral with respect to y, and here are its limits. It goes from 3 to 3 plus the square root of 25 minus x squared. Then the outer limit is x varying from -5 to 5. As I mentioned before, if you have constant limits of integration and you have a continuous function, then it doesn't matter what order you do the integration. You could integrate with respect to x first and then y, or with respect to y first and then x. However, when you have limits that are functions, the most outside limit has to have the constant values, whereas the inside limits can have function values, and the functions can depend on the outside values. What that is shown here is that the inner one is y, and its limits are functions, and they are functions of the outside. The reason for that is that once you've taken this limit, the integral with respect to y, once you've taken the integral with respect to y, you will now have an integral with respect to x. Then you can carry that out and finish the problem. So here is this integral. We have the y on the inside, and its limits are functions of x. At least the upper limit is a function of x. So we carry this out assuming that all the x's are constants. By the power rule, y integrates to y squared over 2. So we carry out that integration, and we evaluate it at its limits. Right? And here you see its evaluation at its limits. This would be the upper limit. Let me mark this up a little bit differently. So here's the upper limit. And when I evaluate y squared at that upper limit, the upper limit comes down in here, even though it's a function. You just x as though it's any constant. And then the lower limit, which isn't necessarily a constant, but in this case is here. So you follow just the same rules as you do before, only you will have perhaps a variable in those limits. Now you can work that out and integrate it, but now you see, once you've worked this out, you have, oh, what happened to the x? Just a minute. This is dx on the end, just like it is here. But now you have, when you get done with this first integration, now you have an integral with respect to x only and constant limits, and you can carry that out. You see that you could not change the order of these limits as it stands. It is possible if the limit is if this function is continuous and the function that you're evaluating is continuous. If everything's continuous, you can change the order, but you don't just mechanically change it and put the x's on the outside. You have to go back and look at your original diagram and find new limits. And that's the subject of another lecture. So what I'm saying you cannot do is this. You cannot go and then integrate dx dy. You can't do that because the most outside limits have to be constants. And this slide is just the ending of that integral that was started. In the other case, here you have, of course, your limits going from 5 to minus 5. You're integrating only with one variable, dx. You go ahead and carry this integral out, and, well, actually this one's a little bit more work, but you can do that. You see, now with the constant limits, you can evaluate it. And this is just a slide that says what I've been saying throughout this lecture. The limits can be written in either way if Fubini's theorem is satisfied, which says that the function is continuous and the limits of the function are also continuous. But as Thomas pointed out, finding the limits of integration can be more difficult than evaluating the integrals themselves.